that subscribe button right under the video and also the bell icon to get notification on any of our latest updates on the videos.
This is another Smart View Guides tutorial on working with Excel. Now, the narration of the question says, chemical, civil, and mechanical engineers must often determine the power required to pump a fluid through a series of pipes. To do so, you have to first determine a friction factor. If the fluid flow is turbulent, that is, the Reynolds number is greater than 2300 and the pipes are smooth, factor can be determined as F equal to 0.0396 Reynolds number raised to the power of minus 0.25. Now in this equation, F represents the friction factor, a positive value that does not exceed 0.1. And RE represents the Reynolds number, which is a function of the fluid properties, the pipe diameter, and the nominal fluid velocity. Now for the laminar flow regime, RE less than or equal to 2300, the friction factor may be determined as F equal to 8 over RE. And the RE increases with increasing fluid velocity, U, where rho is the density of the fluid, D is the diameter of the pipe, and mu is the fluid viscosity. And we're given some reference data. Fluid density at 25 degrees Celsius is equal to 789 kilogram per meter cube. Fluid viscosity at the same temperature is equal to 1.2318 times 10 raised to the power of minus 3 Pascal seconds. And the diameter of circular pipe is 5 millimeter, which is the same thing as 5 times 10 raised to the power of minus 3 meters. We're also given the formula for fluid velocity, which is volumetric flow rate divided by cross-sectional area. The volumetric flow rate here is in meter cube per second, while the cross-sectional area of circular pipe is in meter square. So the question is, using Excel, calculate the values and fill up the following table with reference to the given formula and data. Now the table is this, where there's a space for pressure difference in kilopascal, volumetric flow rate in milliliter per second, fluid velocity in meter per second, Reynolds number, and friction factor. Now we're given volumetric flow rate in milliliter per second, but you know in the formula for fluid velocity, volumetric flow rate was expressed in meter cube per second. So we could create another column in between this and this to convert these values in milliliter per second to meter cube per second. Now we can put in the given data. We have our density in kilogram per meter cube, that is 789, viscosity in Pascal seconds, this, and diameter 5 times 10 raised to the power of minus 3 meters. Our cross-sectional area will be equal to pi d square over 4. We can take our pi as 3.142 multiplied by our d squared, d raised to the power of 2, and then divided by 4. As for the volumetric flow rate in meter cube per second, these are just the given data. The volumetric flow rate in meter cube per second can be gotten by converting this milliliter to meter cube. 1 liter is equivalent to 1 times 10 raised to the power of minus 3 meter cube. So a milliliter, which is 1 times 10 raised to the power of minus 3 liter, is the same as 1 times 10 raised to the power of minus 6 meter cube. So to convert each of these to meter cube per second, we'll just relate them by saying equal to. We can put the cell address of this, then multiplied by 10 raised to the power of minus 6. So this is our volumetric flow rate in meter cube per second. To replicate, since it's the same operation, you can just drag this down to get the values of the rest. As for the fluid velocity, we are going to relate it with this. That's our volumetric flow rate in meter cube per second divided by our cross-sectional area. Now remember that when calculating the fluid velocity, the cross-sectional area will be a constant value that will apply to all these. So when writing our formula equal to volumetric flow rate divided by, when writing the cell address for cross-sectional area, will impute a dollar sign before the name of the column to indicate that the column is constant before we put our cell address. The dollar before E indicates that E is constant, and a dollar before 1 indicates that row 1 is also constant. So we have this, press enter, and then we'll replicate it all down. Then to calculate our Reynolds number, we'll have equal to rho UD over mu. Now our rho is a constant value, our U is not constant, our D is a constant value, and our mu is a constant value. So we'll have to take note of that. So we can write our formula here. We can put those components at the numerator in a bracket. So we'll have rho, which is a constant value, so we'll impute the dollar signs. One here, multiplied by U. For the first value, it's this, then multiplied by D, which is another constant value. We'll impute $2 signs. And divided by mu, another constant value. Press enter and it gives us a value, and we can drag this down. Now remember that in our question we were told that if the flow is laminar, there is an equation for the friction factor, and if it is turbulent, there is an equation for the friction factor. It's now left for us to check our values of Reynolds number, whether they are greater than or equal to 2300 or whether they are even less than. Now this is the same as 631, this is 732, they are all less than 2300 except the last one, which is exactly equals to 2300. So it shows that all the flows are laminar. So our friction factor will simply be equal to 8 divided by the Reynolds number. Press enter and drag it down. Now we are through with the part of the question that asks us to fill in the values in the table. Now the second part of the question asks us to plot a graph of pressure drop against volumetric flow rate in either milliliter per second or meter cube per second using the results in A. That's this, using Excel. Then we are supposed to assume the relationship between the pressure drop and volumetric flow rate is linear. Then we can develop an empirical equation using Microsoft Excel regressions. So we can look for a space and then click on insert, go to scatter, and you can choose this. And this gives you a blank graph or chart area, which is sometimes easier to work with because you can select which values are on your x-axis and which ones are on your y-axis. So you right click and click on select data. You add. You can name the graph. For example, this can be graph of pressure drop against volumetric flow rate. The values on the x-axis are the values of the volumetric flow rate, because in the question we were told pressure difference against volumetric flow rate. So you can choose anyone. You can choose the one in milliliter per second, for example. You highlight them. Then for the y values, you go to pressure difference and you highlight the values. It gives you a range. And you press an OK. OK. Now this gives you a plot of the points. Then we can add a trend line by right clicking and clicking on an add trend line. Some options come out and you click on linear and then go down and click on display equation and chart. So this is our line and this is our equation. Y equal to 0.962x minus 3.3323, showing that when you compare it to the equation of a straight line, you have y equal to mx plus c, showing that our m, that's the gradient of the line, is 0.962, and our intercept, if you are to extend this to touch the y-axis, it will touch it at the point minus 3.3323. That's all about the graph. You can also add the chart elements, that's the axis titles. The horizontal axis is for the volumetric flow rates in milliliters per second. That's this. And vertical axis is for that's all about this part of the question. So for the next part of the question, we have, based on the model proposed by Karaman-Frankel, if the fluid flow is turbulent, that is, if RE is greater than 4000 and the pipes are smooth, the friction factor can be determined as 1 over root F equal to 1.930 log 10, then into the log to base 10 of RE multiplied by root F minus 0.537. Now, if we had only one unknown here, we could just use our solver to find the unknown. But then we have an equation that has an unknown on both sides of the equation. There's no practical way to factorize them together or bring them together and then make them subject to the formula to get our answer. So we're going to use the process known as iteration, and by this we can actually make the f on this left hand side the subject of the formula by taking the inverse of both sides, so that this turns to root f and this turns to 1 over all this. And then to make f subject of the formula, you can square both sides so that you have f equal to 1 divided by all this and then all squared. So for part of the question, that for Reynolds number greater than 4000 iteration, we can impute our values of Reynolds number here down this column, and then we'll have to assume an initial value of f and then impute the formula for f so that this value will be in terms of this value. And then we continue, we copy this value, paste it here, and we continue with the calculation on the right side until we have comparable values on both cells on the same line. So for the first one, we have RE equal to 5000. We can assume an initial value of f. We can pick a small number, for example 1, and then we impute the formula. So the formula is a bit long, so it will be better if we write the formula up here. So our formula will be equal to, remember we are squaring everything after imputing the formula, so there should be a big bracket here, and then the numerator will be 1 because you have taken an inverse, then divide by all those stuff at the denominator. That's, we can put them in a bracket, 1.93, then log multiplied by log to base 10 of our RE value. Now our RE value will be constant for the iteration of this value, so we'll attach dollar signs. RE then multiplied by F. We are going to use this assumed value of f here. Then when you close, it's raised to the power of 1 over 2, which is 0.5. You should take note that if you decide to put this in fraction form, you have to put them in a bracket like this, because if you don't, Excel follows mass and it will just say this raised to the power of 1 and then divided by 1 over 2, which is not the value intended. So you can close this bracket and then minus 0.537. Then you can close the bracket for the denominator and then close the whole bracket for everything and then raise to the power of 2. So you press enter and this is your calculated f. These values are not comparable, so you have to take this calculated value as your new assumed f. You come up here to the formula bar, you copy the value. After copying, press enter and then come to the side and paste it. Now you can drag this down to repeat the procedure and it will give you a new value. Since it's a computer, it will recognize that this is a pattern. So if you drag this down, it will give you values and you can drag this side too. So you compare the two. This is 0.03672518, 0.036738. They are not really too comparable, especially considering that in the question you were told that leave all solution and for significant figures. So you keep dragging and drag this one too. Here you have 0.03674 and 0.03674. You have your four significant values intact, so you have your value of f, that's the friction factor. When you want to do the same thing for the other values, for example, we're asked to calculate up to 25,000. So for 25,000, the value could be anything. You can assume an initial value of maybe 2 and then impute your formula here. That's equal to an initial bracket 1 divided by another bracket for the denominator, then 1.93 multiplied by log to base 10 of your Reynolds value with the dollar signs multiplied by your assumed f raised to the power of, let's say, 1 over 2 in bracket. And you have to close the other bracket and then minus 0.537. Then you close the bracket for the denominator and then close the bracket for everything, then raise it all to the power of 2. Down here, your new assumed f will be a replica of this. Copy it, press enter, and then come here, paste it. Then you replicate this operation, then you replicate this, and you replicate this. Then you check whether they have comparable values. Of course, they have 0.024447, 0.024447, which when you approximate will give you 0.02445. So that's all for this. However, the previous procedure we followed gives us a step-by-step iteration, and there's actually a more direct way to get results quick and faster, and that's by enabling iterative operations in Excel. So you can go to File, in the file you go to Options, and there you go to Formulas and enable iterative calculation. And there's a space for maximum iterations. So instead of a one at a time iteration, it will give you as much as you want. It will just give you a harmonized set of values. So you press OK, and then you can create spaces for the Reynolds number, the assumed f, and the calculated f, which will be a function of the formula. So for the assumed f, you can put values of 1, even though the actual wouldn't exceed 0.1. For the calculated, you insert your formula here, 1 divided by denominator, which is 1.93, multiplied by log to base 10 of the Reynolds number, multiplied by the assumed value of f raised to the power of 0.5, close this, minus 0.537, you close this also, and you close the first bracket, and then take it all to the power of 2. So you press enter and you have your value. Then you can note that we didn't put the dollar sign for the Reynolds number value because for each row there's a different value of Reynolds number, and it doesn't really matter in this process. So you can drag down and repeat the procedure for the other values, but then the trick lies here. You go to the cell for the assumed f, then you press equal to, then you put the cell address of the calculated f, then you press enter. If you don't enable iterative calculations to return an error bar, but now that you've done that, it will give you a set of comparable values. So you press equal to here too, do the same thing here also. And that's also, you can do this operation in a few seconds or minutes.